Okay, so all right, so I'd like first of all to thank the organizers, Cristina and Francesco, for inviting me to give this talk. So I will talk about Neutrinos brothers, who are Axions, and okay, here is the pointer, and really about some very specific topic, which is Axions from stars, so action from stellar sources. And well, I'll try to give an overview. Maybe several of us here are not very experts on Axions, so I'll try to give a little bit of an overview, but given time constraints, I want to especially focus on the topic I'm supposed to discuss, and especially about some recent, like give a panoramic of the recent results. That's what I aim to do. Many results are also not mine, of course. So will be a panoramic. But so we know neutrinos. We know are examples of light weakly interacting particles. They're fermions, right? So axion-like particle may be thought as similarly light weakly interacting particles, which are pseudoscalars rather than fermions. Okay, so and these axion-like particles, which are also known as ALPS, axion-like particles, right? They are Oscar. Let me see. Sorry, they are they emerge from several theories beyond the standard model, are motivated by several extensions of the standard model, and they also have an impact in particle physics, cosmology, astrophysics. So very, very interesting. There is a lot of research going on in these last years to detect them. And we are actually now finally exploring the parameter space which is motivated, physically motivated. So maybe we'll discover them. Okay, so they can be dark matter candidates. It could be a great discovery. So the most, the best motivated axion-like particles are actually axions, or QCD axions, which were introduced to solve the strong CP problem in the strong interaction. So I'm not going to discuss that problem, but somehow they were introduced to solve a fundamental problem in particle physics, and they're also dark matter candidates. So very, very well motivated. There have been some recent reviews on axions and axion-like particles, which I recommend for anybody who wants to get a little bit more information about these things. The last one is actually a recent review on axion astrophysics, which covers part of the topics I will discuss here. So just some minimal introduction. Essential for us is that axions and ALPS, in general, we use the word ALPS, interact with standard model fields, and so we can do phenomenology with them. So they're right. So in particular, they interact with photons and protons, neutrons, and electrons. This is for from a phenomenological point of view, these are the most relevant interaction vertices. Okay, so they interact with the standard model fields, and therefore they can be produced in stars. And if you take a strongly interacting particle like photons, suppose, right? Photons also are produced in stars, but then they scatter, right? And okay, Phoebe was supposed to be here. A feebly interacting particle instead is produced in the core of a star, and then free streams to us, similar to what neutrinos do. So they can be stars can be very efficient in producing them. And because they are feebly interacting, so this weakly interacting property is actually beneficial for the case of axion of a stellar production. So now there has been a lot of discussion about stellar production and bounds that one can set from this, but I'm not going to discuss that again because I want to restrict to detection of these stellar axions. Okay, so this is pretty much the premise. This is a recent plot from Pierluca Carenza. It's a paper in preparation where he's actually compiling the flux a map of the flux of axion-like particles from all stars. So here we have the sun, and this is a production in the magnetic field inside the core of the sun. So I will mention this briefly later. And this is the production from the sun through scattering of the electric field of the ions inside the sun. Photons converted into axions in the electric field of the ions of in the sun. This is the flux expected from all main sequence stars. This is from supergiant. This is an example of a flux from Betelgeuse, so a more massive star further away. This is from a supernova at 10 kiloparsec. And this is the diffuse supernova axion background. And obviously there is a choice of the coupling was made to make this plot, and the choice is at the level of the current, roughly at the current bound. Okay, so let's start with the sun. We heard about the sun in the previous talk, and we'll hear more about the sun in the next talk. The sun is the closest star, so we have to study it as well as we can. And so axions can be produced in the sun. When I talk about axion, I normally means all axion-like particles, right? I use interchangeably the two terms. Okay, in most cases they're interchangeable for what concerns us. But so they could be produced through coupling with photons, with electrons, or with the nucleons, right? In the case, and okay, so here is a summary table. But the key point that I want to point out with this slide here is that you can produce axions with quite a large range of energies that go from EV to MeV from the sun, and through different processes. Now I will focus mostly on this, and in the backup slides I have some discussion about possibility of producing axions also through nuclear reactions, which is a topic which has been revitalized recently. So there are recent results and proposals. So this is quite new. Unfortunately, I have to cut somewhere. But these are the mainstream for sure sources. Okay, and I will focus on those unless then we want to discuss. So if I look at the production, production through, oops, I get confused about that. Okay, so if we look at the production through axion electron and axion photon coupling, we get this spectrum. So we have this processor called ABC, atomic, Bremsstrahlung, and Compton for a specific coupling, which is this blue here. And then we have this Primakov production, which is the conversion of thermal photons in the core of the sun into axions in the electric field of the ions and the electrons. So this looks slightly different, and there is actually quite a bit of discussion now in the community about possibility of distinguishing them. Obviously, you need some energy resolution, but it's not excluded. We're discussing that. Maybe if I have some time, I'll tell you something. But anyway, to give you an idea, at the level of the axion bounds we have now, we expect some 10 to the 11 axions per square centimeter per second on Earth, picked at a few keV from the sun. So just to give a number. And so this is a number that we are able to we would be able to see with the next generation of telescopes that look at the sun. These are called the helioscopes. So it's definitely okay. I'm excited, but then we'll see. Okay, so this is the story. So I think the best way to detect to see these axions is through the so-called CKV helioscope. So the CKV helioscope is a telescope that points at the sun. It has a magnetic field, right? A large magnet, and axions are converted into photons in this magnet. I'll show you a little bit more information about this later on. And they're converted into photons. These will be X-ray photons, because I told you this is peaked at keV. So you need some optics, X-ray optics here. So there you can focalize in a small detector, X-ray detector. So the optics is essentially if you want to build a small detector, which is easier to build. So this was proposed by Pierre Sikivi in 1983, and is the major. I mean, in my opinion, the best, maybe only way, one of the only ways, but it's certainly the best way to look at Axions now, right? The way it works, let me show you some things, right? You convert okay, you convert Axions into photons in this magnetic field, and the conversion is given by this formula here. So it goes like B, and the length of the magnet squared, obviously coupling squared, and then there is this term, right? Which this is a sinc function. This can suppress, and this Q is the momentum transfer, which for relativistic axions looks like this. This is the energy of the axion. This is the mass, and this is the effective photon mass if there is a plasma. And so obviously when QL is very small, this drops, goes to 1. So you have a probability that does not depend on the mass. And so you expect for small masses, here we plot the mass, this sensitivity to be flat, mass independent. Here I'm plotting the coupling to photons, okay? And then at one point, this term for sufficiently large mass, this Q becomes large. So this may become large, the argument, and then this becomes roughly 1, and there is this suppression here. So the sensitivity is suppressed. This happens for the typical energy of solar axions. This happens at about 10 milli-electron volt for a magnet of 10 meters, which is roughly what you have. So let me mention a couple of things also. Since maybe for some of you this is not completely obvious, this is called the parameter space. You normally plot one of the couplings, and the axion photon coupling is the most common. This is the axion mass, and this yellow band is the band where we expect these QCD axions to be. So axion-like particles can live everywhere, but QCD axions, those who actually solve the strong-CP problem, are expected to be here. There is a lot of discussion about this. You can find a lot in the various reviews that I pointed out. It's not like a sharp band, but it's essentially there are arguments, simplicity mostly, argument, but also phenomenological consistency that want QCD axions to be preferred, QCD axions to be in this band. So obviously this is an important target in the axion parameter space. Is an important target. All right, and the possibility to it was actually pointed out in this seminal paper here. Actually, Georg was one of the authors that one can actually extend the region. This is called coherence, where the convergence is coherent, can be extended by tuning, adding a gas in the pipe, and tuning the index of refraction in such a way that this Q gets still again suppressed, so you still recover here a coherent scattering. Okay, and so this can be done, but it's very laborious because you have to scan one mass at a time. Obviously, you have to guess the mass and scan it, but it's possible. So now I'm going to show you the very latest results from the CAST, from the CAST, which is CERN Axion Solar Telescope, which is the best helioscope to date. It's been running for a while. Actually, now they're just analyzing data. This can be the latest, the last analysis they do. I'm not sure, but this came out a couple of weeks ago or something. I mean, very recent result. They get to this point. There is actually there are actually astrophysical bounds that are a little bit stronger, but obviously the systematics are larger for astrophysical bounds. So this is quite important achievement, and they got this bound. As you see in the previous run, they actually also did this extension of coherent conversion using this gas, and as you see, is a little messy, but this is the idea. So this is the CERN Axions Solar Telescope. There is actually now an effort to build something better, bigger, more expensive, but it's moving on. So this is called now Baby YAXO. This is the next stage. Okay, the idea of a YAXO means International Axion Observatory was proposed, maybe 15 or so years ago, 10, 15 years ago. More recently, the collaboration decided to go for something a little bit smaller and more affordable in terms of funds, which is called the Baby YAXO. So the name is very intuitive. And Baby YAXO, so this is cast. Baby YAXO can already probe quite a bit more parameter space unexplored, beat by far the astrophysical bounds, and also explore the QCD axion region. And this is going to be built now in DAISY. So this is not science fiction anymore. And YAXO is still the aim of the collaboration, obviously, to get here because you can do much more interesting stuff using YAXO. One thing I want to mention is that now also that we have a new experiment that may be run, and we are going to build from scratch. We're also looking at what kind of physics you can do and make hardware choices based on the physics we can do. For example, energy resolution and energy thresholds, like, so I don't have much time to talk about this, but somehow you can make choices that allow to get to some physics, and you have to study them because obviously with infinite money you can do the best, right? But finite money, a finite amount of money, you have to make some choices, and there is a lot of discussion about that in the collaboration. Okay, so then another option to see solar axions is to look for the magnetic field of the sun. The sun has a magnetic field, and so rather than having a magnet, rather than building a magnet, we can take advantage of the magnetic field itself of the sun. So what happens here is that L, well, this magnetic field is not uniform. So the formula I gave you before, it doesn't apply to a magnetic field that's not uniform, right? But it gives you an idea. So here L is much longer, the magnet is much longer. So obviously you gain in sensitivity, but it's also much easier to get incoherent because L is longer. So this sign becomes important sooner. So we already know they will probe smaller masses, right? But then maybe high sensitivity, and then obviously here you get when axions are converted, they're converted into X-rays. X-rays don't go through the atmosphere, so you cannot detect this from Earth. You have to be in space, and you can use NuSTAR. Why NuSTAR? Well, first of all, it can look at the sun, and it did look at the sun. So there is actually a recent paper a couple of weeks ago, again, very recent, where this analysis was done, data that have been there for many years, and very detailed analysis, very careful analysis. Obviously very difficult because especially of the magnetic field, the modeling of the magnetic field. But anyway, there was this paper here, and these are the results just submitted to the archive. This is CAST, to tell you, right? This is NuSTAR, like quite a bit improvement in sensitivity. You can see this, by the way, this is Baby YAXO. This is YAXO, and this is another experiment which is currently running at DAISY. It's called ALPS2. So a NuSTAR, as you see, micro electron volt, and then loses sensitivity, but quite impressive result. So okay, going almost okay on time. Now there is also another way to probe solar axions, and this with this large underground dark matter detectors, which we are learning, they can do everything. They can do dark matter, they can do neutrinos. They can also do axions. So maybe we can close everything else and just focus on those. Well, in this case, actually I'm not optimistic at all about their potential to look at solar axions. And the reason is this, right? The way to detect, they look for axions is this axioelectric effect, which is the analogous of photoelectric effect. This cross section, right? So an axion that does the same as a photoelectric effect. This cross section for non-relativistic axions is suppressed by energy over the mass of the electron. Mass of the electron, you know, so half MeV. So this KeV, this is a big suppression factor. So it really kills you a lot, the cross section. So xenon, this is the result from xenon 1T. Then there was xenon NT, which is this. And this is the parameter space. This is coupling two electrons and coupling two photons. So it's this parameter space. But just to give you an idea, the astrophysical bounds, which are shown here, this is the original paper from xenon NT, in fact, are here. I wrote to the collaboration, but the paper was published already. So, but anyway, so the astrophysical bounds are here, and they are here. So it's very far. I know that astrophysical bounds need to be taken with a little bit of a grain of salt, but still, they're very far. Even something like Darwin can be estimated to get here. So for me, this is not the optimal way to see solar axions, at least through this process. But then obviously there can always be surprises or things that one has to consider. This is just my consideration. All right. So then I want to mention another production channel for solar axions, which is through a magnetic field in the core of the sun. So besides the magnetic field outside the sun, which we know exists, there could be also magnetic field in the core of the sun. In fact, there are models that predict that and give some, well, there are models that can be used. So this figure is a little bit messy, but let's just focus on this blue shaded line, which is the expected spectrum from axions produced by conversion of thermal photons in the magnetic field in the core of the sun. And this is quite a decent amount of axions, which perhaps could be observed. This is the Primakov case that I showed before, so this is even larger. The difficulty here is that one, the signal loses coherence already at like milli-electron volts, so you could probe only the small mass region. And the second is that using the current baseline helioscopes, we don't arrive at this threshold. In fact, talking with people in the collaboration, it's possible, not too difficult, to get to this threshold, 300 EV, for example, with baby AXO. But 100 EV is difficult. I mean, it would be expensive. You have to do some substantial changes. So especially for the optics, for the detectors, it's possible, but for the optics, it's difficult. So perhaps this could be something to do in the beyond baseline YAXO. There is this nice paper. There are other papers on this which are actually very interesting, which I can give you references. But I think it's something to consider interesting, but for beyond baseline for sure. Okay. So I need to probably speed up a little bit, but I talked about solar axions so far, and obviously the sun is the closest star, is the one we can study the best. But in some ways, it's quite a remarkable star, right? There are many stars like the sun. It's a main sequence, and most stars are main sequence and look a lot like the sun. So there are other stars. Unfortunately, they're further away, but the axion flux decays like distance squared, of course. But then the production goes with the high power of the temperature. So if one has a star which is much hotter, maybe it's a little bit further, but maybe this can be compensated. It's at least worth looking. So in my opinion, I think it's good to look at supergiant stars, which are much hotter. and they're far, but like we have to try, no? So spoiler alert, it doesn't work, but but let's look at it in any case, right? So there is, by the way, a catalog just this year came out. This catalog of supergiants. So there are several supergiants close by, meaning a few hundred parsec from us. And one thing I want to show is something quite interesting about being able to see supergiants through axions, right? So suppose that we have a telescope good enough to see axions from supergiants. Now let's look at a simulation. This is a messy table, but anyway, a simulation of a star Betelgeuse. This is a simulation of Betelgeuse. We look at Betelgeuse at various evolutionary stages. And when we observe Betelgeuse, we normally look at the surface with normal telescopes. So the effective temperature and luminosity. And so we look at these numbers, and these numbers don't change. So when we look at Betelgeuse, we don't have a way to know what's the evolutionary stage. So it could be burning helium, carbon, or exploding very soon. So this is the time to explosion, by the way, right? We show this, right? So we don't really know this because when we look at the surface, we really don't see anything changing. Now, if you produce axions, you can produce this through this mechanism, say, no, and you can parameterize the production with some form, which fits really well, and you have some parameters, for example, DC or these average energies, and then you look at those, and they change. So without now, obviously, looking at all these numbers, right? What I care to show is that if we were able to see axions from these stars and see a few of them, enough to reconstruct a little bit the form of this spectral form, we would know where the star is in the evolutionary stage, right? We can do the same with neutrinos also, but neutrinos become important later, at carbon burning, right? Axions are already important, become already very important in helium burning stage. So in some ways, they are really the best telescopes for supergiant stars are axions, right? If they exist and they're coupled strongly enough so we can see them. No, right, 5, come on, like a little bit more. All right, let me. Okay, I'll try to speed up a little bit, but let me just show you a little bit of the like estimates. You can calculate that in the sun you produce 10 to the 39 axions per second. In Betelgeuse you produce many more, but given and higher energies, but given the distance, you see only about 1,000 axions per centimeter square per second on Earth, and this is way too little to be seen. So I just want to mention, so there is no chance now or in the near future. But axion could convert into photons in an external field, and there is an external field between here and Betelgeuse. There is a galactic magnetic field, which is about microgauss. So if you do, so if you use this conversion, then suppose we can neglect this part, the distance drops. So you have, the probability goes like distance squared. So okay, so this is fantastic because at that point you have photons, and like the photons are very easy to see. Okay, so in principle, this is not such a big. This actually is 6.5. So this quite. It's not such a big suppression, I would say, right? So you see a ton of photons, and this is very good. The only problem is that if this can be ignored only for very, very light axions because D is very large, and so you lose coherence very quickly. So you get to this result, which you can essentially probe a very a region only for very light axions, but much better than cast, of course. Like so the sensitivity is good, but only valid for small masses. So this idea of probing using a magnetic field to see axions is actually quite important. Okay, so now just in the last few minutes, I want to mention about supernova axions And there'll be a lot of talks about supernova, so maybe here I can go a little bit faster. But anyway, supernova are the real monsters. They're like properties that are completely different from other stars. You can produce 10 to the 56 axions per second, which corresponds to 10 to the 13 per centimeter square per second on Earth. So more than from the sun, 100 times about more than from the sun, but only for 10 seconds. So you cannot do an observation of a year. This is one problem. Second, when the supernova happens, then in 10 seconds it's gone. So if you want to point, either you have a big, like, you know, a Cherenkov detector or something that's isotropic that can see things coming from everywhere. But if you want to point, you need to know in advance where to point. So you can rely on these news, for example, this alert system. But there are still issues there. So I rely on my colleague Cecilia Lunardini for this. and she wrote a very nice paper about how well we can detect pre-supernova neutrinos and let you know where to turn when, and with some angular, unfortunately, fairly large error in the angles. So you have to check that there are not many candidates there, but it's a possibility. So this has been explored. So when you go to modeling axion production in supernova, right, you have three main channels: Primakov, Bremsstrahlung, and then this pion process, which was mentioned also yesterday. And this may actually dominate. So, except for this I think is fairly, well understood. These two all have like difficulties in modeling. And in this case, for example, there are many difficulties related to the abundance of negative pions in a supernova. There was this recent paper, not published yet, which studied the expected spectrum from supernova axions. And as you see, this okay, the Primakov production can be neglected in this case, but you have the production from Bremsstrahlung and then the harder spectrum from pions. If we could detect, obviously this spectrum depends on the pion abundance in the supernova, and so detecting this spectrum can be a way for us to find this value, which is not so easy to predict. Somehow there are many uncertainties. Okay, so I went a little bit quick, but I want to tell you that there is huge effort in recent years. These are all like papers from the very last couple of years of strategies to detect these supernova axions. There is a new proposal to do this with the helioscope. So pointing, and I guess let me just skip to this. You can go. The best way again is the best chance is that these axions are very light, and so they are converted into photons in the magnetic field from here to the supernova, and then you see it with like Fermi-LAT or something like that. In that case, you can really probe a large region of the parameter space. If they are not, you can still see, even without conversion, you can still see them with a helioscope. But okay, maybe we can discuss this plot later. I mean, it's not much time to discuss it. I just mention you see very few events if you're lucky. If you're very lucky, you see very few events. So maybe you can do some reconstruction about understand some things about the supernova. If you're very lucky, if you're using the full YAXO, but certainly you're not going to see many events, if at all. So it's a little bit, but you can probe a large region, interesting region of the parameter space, including QCD actions. So this is quite interesting. So last slides, very last, like 2 or 3 slides. Just want to mention some very recent papers that came out a few weeks ago. One is from Safti and Claudio Manzari and his group, Safti's group from Berkeley, and they consider the possibility that the supernova has its own magnetic field. So if a supernova has its own magnetic, like the progenitor, no, has its own magnetic field, then this magnetic field is actually going to be much larger than the magnetic field than the galactic magnetic field, and has a shorter length. right? So from the formula we've seen before, we're most likely able to probe larger mass range, right? And have some sensitivity, but especially expand the mass range. So what they claim is that you can actually push these previous bounds were like here, say, no? Yeah, supernova, this was the previous bound. They can actually push it much more in mass. Okay, so this is an interesting idea. The problem is, obviously, you have to make some assumptions about the magnetic field of the progenitors. And, you know, they're taking, I don't know, 100 Gauss, or I think they're between 100 and 1,000 Gauss, which may be too much or something, I don't know. Here they also show cases where this is only for axions produced through Primakov. They're showing also cases where axions can be produced through these other processes, so which would be even more. But then one thing they propose, which I find it interesting, I don't know if York, for example, or somebody have an opinion about this. They propose these galaxies, which is because they claim that if a supernova goes off and you want to observe it with the Fermi-lat, you have only a 20% chance to see it because it lasts 10 seconds and maybe Fermi-lat is looking somewhere else. And actually, when I talk to people from Fermi-lat, it's not that they change direction. Like this does a scan every some time of the entire sky, and so even if you have an alert, maybe they don't turn, and then you miss it. And the supernova, like a galactic supernova, are such rare events. So that would be a shame. So they think we can have a network of 4 or 5 of these Fermi-like satellites, and then we would not miss it. And besides, we could see maybe some extragalactic cases, right? So you could get, even without a galactic supernova, you can get still some interesting physics out of it. Now, price tag very high. But then I talked to Benjamin Safdie, and he said, yeah, but maybe we can build them a little smaller or something. And because the price tag of Fermi is very high, but also because it's big. And it goes very, very rapidly up with size. So one last thing is that, again, Benjamin Safdie, again, very recently, like just a couple of weeks ago, like, a month ago or something, I don't know, proposed the possibility to look also at extragalactic axions. If you can look at the entire galaxy, and there are some galaxies, there are some galaxies that are particularly good for producing axions because they are starburst. So they have a lot of young stars. Young stars are hot, like Betelgeuse. And they can produce a large amount of axions. And besides, they may have large magnetic fields. And a galaxy like they consider M82, for example, will look like a point in new star. So they can just do point source analysis, which is relatively simple. And therefore, they think they may actually see maybe axions even from extragalactic, like from entire galaxy, which is far. And they claim very strong bounds. So to give you an idea, this supercluster is essentially the same as Betelgeuse I showed before, so they can go further down. And okay, so I think I want to finish with just two comments. One is that axions, if axions exist and they're coupled strongly enough, we can use them as messenger and learn a lot of things about the sun, especially, for example, solar chemical composition, temperature profile, maybe solve this problem that Francesco will discuss in the next section, I don't know, and also supergiant evolution, things like that, right? So this is obviously quite exciting, and I think we should, there's been a lot of work on this, learn about the magnetic field inside the sun, like really like find out the profile. So it's nice to do this kind of work, even though we don't know if axions exist and we don't know the coupling. And the last slide is my 2 cents on will we detect stellar axions in the near future? And I think there is a good chance. Obviously, if they don't exist, we're not going to detect them. But there is a good chance to detect, if they are at the current stellar bound, there is a good chance to detect solar axions using helioscopes. And so we'll see, because this will have data maybe in a matter of years. It's unlikely a discovery through the coupling to electrons. with any experiment I know. There are several channels through coupling to nucleons, which I didn't talk about. Well, because of time, but there is a lot of effort, experimental effort to detect to this channel. I think they're still far, like in tension with supernova D7A bounce, so probably not very likely. So supergiant, well, if axions happen to be very light, then this could be a good way to detect them. There are like order 10 supergiants close by, which one can look at. Maybe one of them is in late stages, produce a lot of axions. They convert, and we see them, but they have to be very light. And from supernova, direct detection may be difficult, like with the helioscope, where you point and you actually see the axions. That could be difficult. If you're lucky, it's possible. And but if axions are very light, again with Fermilat, you can really explore a very large region of the parameter space, and you would see so many that you could actually understand a lot of things about the supernova, like for example pion content or things like that. So I just want to publicize a little bit this. This I promise is really the last one. Cosmic Whispers. Maybe some of us for sure are part of this group. It's led by Alessandro Mirizzi, and we do a lot of networking, and it's very nice. And there is a lot of effort in this collaboration to study axions, including astrophysics and experimental searches, etc. So I leave you with this, actually with this, and thank you very much. 40 minutes. 40 minutes. Please, yes.
Thank you. So I think that from the point of view of the QCD axion, like a cast type bound is most important. And then I have been seeing this projection of the IAXO for a long time, but I didn't know this baby version. So what is the status of towards the IAXO? Like, is it this baby IAXO exist or?
No, but is going to exist.
Do you have any time frame or?
Time frame, I think before 2030.
2030.
And because at DAISY, I mean, everything is moving to go toward the search. I think there is well, now the very details. I don't know. I only know that one problem is the magnet. The big issue is the magnet. Obviously, here we're talking about something much easier to build than full YAXO. But when I talk to the spokesperson, they're very optimistic now about about actually going on and starting construction. So I think if you ask Igor, as I do, they will tell you maybe 2028, like already build something soon.
And you said the cast is running, right? So
well, cast they have data. They're doing data analysis.
I see. Okay.
And maybe this data. Maybe I don't know if you know more, but this data, they have this data and they did this analysis right now. Maybe the last analysis they do at this point, I don't know. Yeah, now it's shut down. It's not running anymore, but they have this data that they're analyzing. Yeah.
Confused that you have.
No, but this is data they had that they did the analysis.
I see.
Yeah, obviously shut down for a long time. Francesco, yeah.
So if I don't know if I'm wrong about that. 10 to the 11 axion per centimeter square per second with KV energy approximately should correspond to 0.1% of the total solar luminosity. Is this number?
No. It's less. It should be less than that. Yes. Should be less than that because there is a bound which is at about 3%, which is your bound, no? With Serenelli and yeah. And this is but this would be more axions than that. So this is a little bit this now. I mean, these are approximate numbers, right? But if you look, we can look together. But essentially, the 3%, which corresponds the 3%, which corresponds to the possible cooling bound from the sun, like like energy loss, anomalous energy loss allowed from the sun. This should give you like a larger coupling. So this should be less. Now it's possible that I did the estimate. My estimate is all right, but essentially for sure the number is because I'll show you here. Essentially, this number. So this is assuming. Oops, here, right? This kind of a coupling, right? Roughly, no, and the bound that you get in your paper is not quite as strong as this, right? It's like maybe something big.
I don't remember. I was just asking because
it's not too far, maybe from that.
yeah,
It's not too far from that, but it satisfies the. It does satisfy the minimal, the maximal energy loss that you can lose through anomalous channels from the sun, essentially.
This 10 to the 56 axions from a supernova.
Yeah, this is a rough estimate based on 10 to the 53 ergs. So saturation, and then assuming a pretty much 100 MeV each. So it's an estimate made like this. Depends obviously, the real number depends on how many axions you don't know the coupling. So this be maximal, and also depends on what energy they have. Right.
Volpe and then Gianni.
Yeah, on this issue concerning axions from supernovae, what is you mentioned several works.
Oh yeah, many, yeah.
Yeah, so yeah, there are many in the literature. I wanted to know what is and before you mentioned the magnetic fields in pre-supernova, but if the process involves magnetic field in the supernova, what is the minimal magnetic field you would need to have a significant effect?
So
I mean, obviously depends on the couplings, but
no. So okay. So the results I've shown, I think they talk about 100 Gauss to 1000 Gauss, but they don't really. I mean, they don't really know so well. But they, it's more like theoretical assumptions, and so in the paper they say that actually 100 Gauss would be very conservative. 1000 Gauss is more likely, but I don't know how strong these considerations are, obviously. So I guess, but these bounds that they show are based, I think, on order 100 Gauss.
Okay, thank you.
Aldo, yeah.
Yeah, I have a question about the supernova axion. So you mentioned the axioelectric channel in dark matter detectors. I think if this is a concrete detection channel, and they are these low energy electron recoil detectors, they really can probe. Maybe they are very important because to deploy several satellites around the Earth, maybe it's too expensive.
Yeah.
On the contrary, these detectors, for other reasons, are going to be built and are already built. So it could be an effective if
this is an excellent point, and I'm thinking about some of these possibilities. So one of the problem is that photoelectric. So so for supernova, would be ideal also because you don't have to point or anything, right? So, so this axioelectric is probably not the ideal because consider these have 100 MeV energy. So photoelectric is not the ideal maybe process. So you may want to look at other processes that can happen from Compton or maybe pair production. When you have this in the material, so it's definitely something quite interesting, and there is I don't think a lot of literature on that. There is some literature on like with Cherenkov detector, for example, but also there
because this paper that you mentioned is about
which one?
I think I understood that from xenon collaboration.
But this is from the sun, though, eh?
No, but I'm considering the same detector for a supernova.
Yeah,
action
I just
through the same channel.
but axioelectric. So the photoelectric, when you look at the photoelectric, right, which axioelectric is similar. No? So when you look at photoelectric, it really drops down at high energies. So when you go to 100 MeV energies, it's not the ideal
Okay.
process.
This is the point. It's not
Yeah,
ideal.
yeah.
This,
But I can tell you this: if you want to detect 100 MeV photons, the axions and photons somewhat similar, let's say, no? If you want to detect 100 MeV photons, what you do is you look at pair production. So that's what I'm thinking now.
Okay.
Somehow something like that.
I see this point, but they don't need any direction.
Yeah. So this needs to be explored for sure. Yeah.
By the way, the last lifetime of CAST, did they deploy the microwave cavities inside the magnet?
They're doing RADES, no? They're doing these.
So
Yeah.
this was RADES is already completed.
They're running. Yeah.
It's in operation
In
the CAST magnet.
with CAST, yeah, that I know, yes, right. I mean, I think their data, right? Yeah.
It's a different kind of.
Well, it's well, you use the cavity, so it's not quite the like has nothing to do with the sun, right? You know, it doesn't have to turn or anything, but it's a big cavity with a magnetic field, and so you just.
Because cavities are also in IAX, they are also considering possibility.
Yeah, for sure. Of course. Also with baby AXO and everything. Yeah, of course. Yes, that you do. Thanks. Yes.
So when you are considering the conversion of the say axion to photon and vice versa, so for say suppose new star or galaxies experiments, what is the like the radius or at what distance these axions can convert into the photons? And also the second question is that if you're considering the axion photon oscillations, the photon can get the mass. And for these studies, are you considering the action of the dark matter, because we need to match the momentum as well, right? Consider the dark matter.
So I'm not sure I was able to understand everything, but let's go to this. Okay, so first of all, this formula is for relativistic axions. So when if you think of dark matter, I haven't considered at all dark matter in this talk because I want to avoid the kind of systematic uncertainties that you have in dark matter. You don't know if axions are the entirety of the dark matter, right? If axions exist, they would be a fraction of dark matter, but maybe not entirely so. But stellar production is in some ways it's easier to predict. So this formula exists for this formula is valid for axion relativistic axions. So if you have astrophysical sources, you use this formula, and I'm not sure if you had a question about this, but let's go to dark matter. There are also cases in which you can use stars to probe dark matter axions, because if stars have magnetic field, these axions can convert in the magnetic field and into photons, and then you can see them. Normally, you would see radio band, right? Because these dark matter axions are like a extremely small momentum, are not relativistic, right? And
yeah,
so
but like you somehow need to match the momentums, no? If you're considering the oscillations between the axions and the photon, and if you consider the axions as a dark matter, which is non-relativistic, but photon is relativistic, so you have to somehow match the momentum to, because you're also considering the axion photon conversions.
Yeah, of course, yeah.
So
You have all the possible concerns. Well, there is a magnetic field also in the game, no? But altogether, yeah, you have to conserve energy, momentum, everything. You normally end up with the radio photons.
discuss.
But we can I don't know if I don't know if I'm answering your question, but obviously you consider there is a different kind of approach for the oscillation, but I can show you papers that consider there are several papers that consider this application to dark matter. Obviously, you need to assume the dark matter abundance, and then you need to assume the magnetic field, which could be the sun, or could be a magnetars, for example. And there are several papers on this. And then you produce this radio signal that you can observe on Earth in the window where you can observe from Earth. So there is a lot done there too. Yeah, for sure.
Another question is what you variation for action photon topic and the accelerator topic.
Yeah.
Lot of what mass of actions you are getting that type of bounds?
So you this
For-
plot
No, where you have shown both the action electron.
probably zero mass. This zero
think-
mass.
Yeah. So, Acha, this is for the zero mass action.
Well, consider that here the mass is important only if it's Boltzmann suppressed in the sun, so several keV. Up to several keV is zero mass.
Okay, so
Yeah.
recently some people are developing MEV gamma ray telescopes, right? MEV gamma ray.
MEV. Yeah.
So
yeah,
you have some ideas to use.
Okay.
micro
So
window?
this is a very the very important point. So there is this MEV gap, no? So for what? Okay, let me mention some things. There are several astrophysical cases where you expect axions to be in the MEV region, and there is not a lot of if you look, I don't have the plot here, unfortunately, but there is a like not very much that can cover efficiently this region. I think COSI was actually as a possible candidate. I think was approved. There have been many options considered, like Astrogram, but then it's not going, and then Amigo X, some of this. So even better than COSI, Gecko, and so one, for example, even if you think of a supergiant star here, sometimes the energy can be like, you know, the average energy can be half an MeV, so you can have the tail to a few MeV, and actually if you go even further in the evolution, like when they're almost pre-supernova, you can have a MeV or few MeV. So there is definitely a case because Fermi is very inefficient at a few MeV. And so there is a case, there is a discussion, for example, in the framework of these cosmic whispers. There is a discussion about this, right? It is like one of the topics we like to present in a white paper that we're writing, like, is about this issue. We need to convince the community to build to put some effort in this MEV region, which is important. And the issue there is that you go from Compton, like efficiency in Compton, and a pair production, right? So it's like right at the threshold when one of the processes dominates. In fact, when several years ago, I remember there was a proposal for an instrument called Compare, which was right there at the MEV and was used both Compton and pair production as detector. One other thing I can add, which I don't know if maybe also overlaps with the question was asked before about new star. The other part that we're missing a little bit is also high, very high energy X-rays. Even at the level of new star, there is not really a follow-up to new star now. And so we have like Athena, we have Chandra, a much lower energy. So some of these things we cannot do with the telescopes that get up to 10 keV or 20 keV, and then they don't see anything anymore. It was a proposal which this I may have. There was a proposal. This I may have in my 1020 backup slides. This was like, this XP came out maybe end of last year or early this year. This is a follow-up to New Star, which is this, much more powerful. And I have some of my friends are working here, and they normally tell me this is exactly the range, roughly the range of New Star, at least the upper limit. And somehow some of my friends tell me it's not very likely that this would be approved. But as I'm saying, I think one important issue for the community for the next 10 or 20 years of development in astrophysical probes is this region, which is from high hard X-rays to low gamma rays, which is very important for feebly interacting particles. And thank you very much.
Thank you.
So I see no more questions. So, or maybe once again.
Very simple. What is the cost of YAXO?
Okay. Well, the point is, I'm involved in YAXO, and some of these things they tell me and then I forget. I think is order 10 million. I would say. No, the magnet is very expensive. But I think YAXO is the baby YAXO. Right, so we're always talking about order 10 million, and then YAXO an order of magnitude higher probably, right? So now exact numbers, this is an order of magnitude for sure. It depends on many things also, no? Like okay, this let me stop here, I guess.
Just fine. I mean, we have our time.
No, I mean about talking about
the price.
prices.
Okay,
yeah. But roughly, I think this kind of price tag.
So I propose to thank Maurizio. We have our time, and then lunch will be served. And okay,
thank you very much. Thank you again.